what we got is I've got a,
I did it read on the blackboard.
oh good, but you didn't take them, you didn't
I
take
didn't
them
have
on.
a pad there today.
I emailed it out to you. I sent it to the whole class. So, what I have up here is, I'll draw the entire schematic. And so we got a transformer. It's a step down transformer. It's a center tap, but I'm not using the center tap, so I'm not going to draw it. So I'm stepping down. If I draw it right. Okay, and it's a 12.6 volt transformer, but we're going to actually measure it. Then I'm bringing this into a full wave bridge rectifier. Oops. And we connect this in the center. And then it's going to be a positive power supply. And then what I have coming out is, then I've got, and I'm using this as, it's going to be ground because I'm going to hook my scope up. And then I've got this hooked up to a 100 microfarad 50 volt capacitor, polarized electrolytic. And then right now we're going to modify this in a minute so I can add the zener. What we're going to do is just see what's going on. So what I've got is I've got a 100 ohm resistor, a half watt, and then I'm running this into a potentiometer, but it's wired to act like a rheostat. So to make a potentiometer act like a rheostat, we disconnect one of the wiper, which is the center lead, to one of the other two leads. Now we got a rheostat. I've got one of my meters connected across the 100 ohm resistor, so I'm using this to protect the pot, because if I accidentally set the pot to 0, at least I've still got a resistor in the circuit. And we're going to put a resistor across it, and we're going to use this as our current shunt. So we're going to measure the voltage drop across it and then calculate the current. But we don't really have to calculate it because it's a 100 ohm resistor. So it's going to be 10 milliamps per volt. So if I measure 3 volts across it, that's 30 milliamps, right? You understand that? So we're going to use that as a shunt, as a current shunt, plus also as protection. What we're going to do after we get this set up is we're going to come in and we're going to add the zener regulator circuit to this. What we're going to do is see what's going on here and see what we're working with before we put our zener in. So this is a 12.6 volt transformer, but what we need to do if we're going to do a real good job is see what we get out of it when we're loading it down to our maximum current that we're going to try to get out of our power supply. So right now, one other thing I forgot to do, I forgot to bring up my camera. So we got 3 meters hooked up here. It looks impressive, but so this is measuring our DC output of our power supply, and this is measuring. This is our current. This is our shunt. This is our current meter right now. So right now I've got 48 milliamps flow. Okay, okay. Everybody okay? Got any questions? So this is, by the way, I told y'all this is the way an ammeter works. An ammeter actually uses a shunt and measures the voltage across the shunt. So about the only thing the meter can really, the actual meter or the A to D converter inside the meter can measure is voltage. So everything that we do, we get into a voltage and then we translate it with the display. Are we okay? This meter right here, what I'm going to do is I'm going to put it across the transformer, and that'll be probably the last time that we'll use it. So let me find those leads. Here they are right here. So it's a 12.6 volt transformer, and we're going to see, and we got it loaded down to almost 50 milliamps. Go ahead and do 50 because that's where we're going to run our power supply at. So that's 50 milliamps right there. And then I'm going to come up here and measure across the input voltage. So this is the AC voltage, and it's measuring 13.7. Now, what I'm going to do on purpose is, so it's measuring 14 volts. And what I'm going to do on purpose is I'm going to come down here and drop the load down. And you see the input voltage is changing. See that? Okay. So this is what we mean. This is what the regulator's got taken care of. So we assume a transformer doesn't drop a voltage, but it does. Not very much, but it drops the voltage. So as I load my power supply, not only is my input voltage changing, but it's going to try to change my output voltage too. So this is my output voltage right here. So notice as I load it down, what does it do? It goes down. As I take the load off, it goes up. So this is what your regulator is taking care of. It's going to take this and do what? It's going to smooth it out, right? You understand that? By going through a regulator, and the Zener diode is our regulator. So our maximum current that we're gonna ever get is gonna be 50 milliamps. So that means what I'm trying to shoot for is 5 volts across my shunt resistor, right? Plus 100 milliamp. I mean, that's 10, 16, 20, and then this right here would be 50 milliamps. So this is my input voltage at 50 milliamps. It's what, 13 point what? Let me get across my transformer again. So this is across my transformer. So it's sitting at 14 volts. All right, okay. And then, of course, if I look across our capacitor, let me get my scope back up. I don't know what happened to it. Scope set it up. And so there's channel 1. And we can see the ripple voltage across the DC. If I can get, okay. So we can see the ripple voltage. Okay, see the ripple voltage. We call that a ripple voltage. And as I got up, what this thing trying to do. And so take the load off. I'm gonna move my ground down here and see if that helps. So as I take the load off, so if I take the load off, then the ripple voltage goes down. And if I add load, ripple voltage goes up. There we go. Somehow I got it off run. No, it's gonna stop now. Scope and light, whatever I'm doing. So, what we need to do is kind of calculate this out. And what we're going to do is try to figure out what this series resistor. So I've got my Zener in here already. I just don't have a resistor for it, and I don't have it wired in. But this is a 12 ohm Zener. This is a 1N4742. Okay, so let's see if it's going to work now. And I'll move the ground down. slip down to the bottom. And you can see when I increase my current, my ripple goes up. When I decrease my current, my ripple goes down. And of course, this is what we're trying to do, or trying to remove this kind of stuff off from our regulated output, right? You understand that? Everybody okay? So first thing we're going to try to do is figure out, so that's a little over 50 milliamps. Let me look it down just a hair. In fact, while we're sitting here playing around with it, I'm going to turn it way down. So our input voltage, what did it drop down to? Around 18 volts, 18 volts, or AC, not our DC. Okay. So let's go ahead and calculate what would the V peak out be? What do we say, 14 volts? Yeah. Yeah, 14 volts. Let me do that. Divided by 0.707. So I've got, what we got? Got anything, Charles? V peak out. V peak out. Got anything, Brandon? You got anything, Kareem? V peak out? $18.4. That's right. So we take 14 volts, and first thing we'll do is divide it by 0.707. 07. And then we'll come up and we'll subtract 1.4 from this because it's a full wave bridge, right? So that's our peak voltage. Are we okay? So that's the maximum voltage I could ever get. The maximum voltage I'll get is 14.8 volts at maximum current. I mean, I'm sorry, 14.4. So we'll make a note of that. I'm using a 100 microfarad capacitor. So if I calculate my ripple voltage with a 100 microfarad capacitor, so what's our formula? I got y'all's formula sheet, right? So filtered unregulated, and we're calculating V ripple peak peak. What does it say we need to do? Okay, so what's our maximum current? 50 milliamps. What's the size of my capacitor? 100 microfarads. And what's our frequency? Full wave. What's our frequency? 120. Good. You need to know how to punch this in your calculator. Odds are, if you got a standard in your calculator, you're gonna have to say 50 milli, right? And then you're gonna say divided by, and then you're gonna open up parentheses, and then you're gonna say 100 micro times 120. Then you're gonna close parentheses. Then you'll hit the equal key. That's why you need to enter that on your calculator. What's that? I don't think so. That would be nice. So I'm gonna clear this. So we got 50 milli, so it's 50, right? Times 10 to the minus 3 divided by, that's 50, what's that? 50 times 10 to the minus 3. That's 50 milli, right? Divided by, I'm going to open up parentheses, and I'm going to say 100 times 10 to the negative 6 times 120. I'm going to close parentheses. I'm going to hit equal. 4.2 volts. See where y'all did wrong, huh? You see what you did wrong, Drew? But you can't put, I don't know what you put it all together. You can't put things together. If I come up here and do it like this, if I say 50 milli divided by 100 micro times 120, that's going to give you the wrong answer. You can't do that, because what it's going to do is going to take the answer of this and divide it by 120. You understand? It's not going to divide it by the product, and that's why I said do it like, I even gave y'all the way y'all needed to do it. So what are you going to do? Huh? Put in 50 milli, then hit divided by, and then open up parentheses. You know where that's on your calculator, right? Yeah, you just can't run that out in a straight line. And then 4.2 volts. So that should be our ripple voltage, right? Around 4.2 volts. Ooh. I'm gonna burn up my pot. So that little got 4.2 volts. Not too bad. It's actually measuring 3.4, but that's not too bad. Okay. Are we okay so far? So y'all understand the circuit? Oh, I didn't show you. So here's the transformer. Of course, it's fused. So there's fuse right there. And then I'm taking the two outside. So I'm not using the center tap. It's over here. So I'm using this just like a regular transformer. I'm using the two outsides, and then it's coming into the center of my bridge. There's the bridge. Here's my 100 microfarad capacitor with the negative pointed this way toward the negative, right? You understand that? Then I brought it down here to get my load. Here's my 100 ohm resistor, a half watt, and then here's my pot. And you can see I've got the two legs connected together to make it act like a rheostat. Everybody okay? Okay, so we know the ripple peak to peak, so I'll bring a calculator up here so I can see what you're doing. That's okay. But you can holler back there, I can tell you. So here's your parentheses.
Yes.
So I'm going to say 50 millis. 50. Where's your engineer number?
Engineer is already on engineer.
No, but you got to enter 50. You just can't put anything. So right here.
Yeah.
So you hit this one
This
and hit
one,
that one. Yeah.
and then -3
Minus 3
divide.
divided by open parentheses.
Yes.
Okay.
100
100 times 10 to the minus 6. You got to put yours in there first. Minus 6. Okay. And then I'm going to put times 120, close parentheses, equal.
Oh, okay.
So
I was putting
we're off
100 close parentheses, and then again I was opening parentheses and putting one.
No, anything you want to group together.
Okay.
Yeah. And
Okay,
this is
there
why.
I was going wrong. That's
Yeah.
all. Okay, I got it now.
Yeah, when we draw and this is, you got to figure out what you do with the calculator. So this is what I mean. So what you were doing, you wasn't doing. So this is what I told y'all to do right here, right? I said enter what? 50 milli. Hit what? Divide by open parentheses 100 times. I didn't put the times. That's the key. 100 times 120 close parentheses, and then hit what? Then hit. So what you were trying to do, you were trying to put it in like this, which is what is the way we do it, Matt. The way you would do it if you was writing it out in algebra. So it'd probably been better if I would have drawn it like the calculator instead of putting that right there. If I'd have put what in there, and if I would have put times right there. But in math, if you put two parentheses together, it means multiplication. So that was my problem. Okay, guys, so what do I need to, so what's my maximum voltage? Well, my Vn max is going to be whatever V peak was. So it's going to be equal, Vn max should be equal to pretty close to 18.4 volts. Because that's the top of the ripple. Y'all understand that? Yes or no? So that's the top of the ripple. My minimum voltage, my Vn minimum, is going to be 18.4, which is V peak out, minus, what did we come up with? 4.1, 4.2? 4.2 divided by 2. So 18.4 minus 2.1. So what does that give us? Is that 16.3? Okay, so that's Vn minimum. Okay. So what we're trying to do now is we're trying to calculate our series drop-in resistor for our Zener. What do we need to know? So we're fixing to add this circuit right here. Well, what happens, and I thought we talked about this, what happens is everything. So you're right, we wouldn't divide this by 2. We would divide it by 2 to count the average. So what we're trying to do, did you hear what Brandy said? Well, no, it doesn't, because what we're trying to do is this is what's going on right here. Now, to calculate our Zener, we need to know this. So this right here is going to be the maximum that it'll ever be, right? And the minimum it's ever going to be is down here. So this will be Vn minimum. That makes sense? So what we're doing, so what we just calculated is we just calculated this voltage right here. We calculated V ripple peak to peak. So in this situation right here, you would be right. we wouldn't divide it by 2. When will we divide it by 2? If we're trying to get the average, right? What my meter would measure. So when I come up here and look at this, so when we calculate this, we know we got 18.4, and then when we subtract the minimum, what's our minimum? What would our minimum be? So VN minimum would be equal to 18.4. This is not on the formula sheet, what it is. We're just doing this like would be what? So what should we, 14.2 those. Now, if I was going to calculate what my meter measured, then we would use 18.4 divided by 2. So the DC average, and this is what the formula sheet gives, the DC voltage that my meter is going to measure is going to be 18.4 minus 4.2 divided by 2. So this is all right. So let's do that. So what's my DC going to measure right now? What's that? Well, you can't say 18 minus 2.1 and come up and get 2. So that's 18.4 minus, so that's 18.4 minus 2.1. So it should measure what? 16.3. Oh, let me load it down again. So here's my meter. This is the one that's measuring DC output. Let's put get it back up to 50 milliamps. Well, I won't wait past it. So there's 50. That's a little over 50 milliamps. We're expecting what? What we say? We'll say, look at that. So we're a little over, and we're measuring. Good gracious, guys! And we're measuring. Here comes 5 milliamps, red. So that's 5 milliamps right there. We're measuring 16.6. So that's not too bad. We're expecting 16.3, and we're measuring 16.6. Not too bad, is it? So right now, it looks like everything that we're doing is basically exactly what we need to get. Okay, so we're going to hook up our Zener, and our maximum current is going to be 50 milliamps. So what do we need to do next? So I've got 12.6 volt Zener. What do we need to do? And we're trying to calculate the size of our resistor. So what we're going to do, thank you, friend, because I was calculating the DC average. So what we're going to do is we're going to we got to put a series dropping resistor in there. We're going to generically call this RS. We're going to put our Zener in there, reverse bias. So this is my positive up here. So I'm going to put my Zener in there, reverse bias. That's the way it regulates. And I'm going to put it in there like this. And then we're going to move our load. We're going to move this stuff over here. We're going to move it over here. So now we should have a regulated DC supply. But the problem is we got to put the right resistor in there. If we put a resistor in there that's too small, we will burn our Zener up. If we put one there that's too big, then it won't regulate. So what do we need to do to calculate that resistor right there? So look at the formula sheet and see what the formula is for RS.
minimum divided by current.
But it's VR minimum, right?
VR
Equals to, what's that? Not VR, Rich. No, that's right. So what's VR minimum equal to? So this is the voltage drop across the, so what we're going to assume is we're going to assume this guy right here always drops 4 volts. And we're not concerned with this circuit over here now because it's in parallel. Because so whatever's across the Zener is going to be across the load. Right? Y'all understand that? Yes or no?
No.
If this is 12 volts right here, if this is 12 volts, and if the voltage drop across this guy is 12 volts, what's going to be the voltage drop across that? It's a straight piece of wire. So if I've got 12 volts, if I measure 12 volts from here to here, if I go over here and measure, I'm measuring at the same spot. What should this measure? So, okay, so 12 volts. So it means I got 12 volts dropped over here on the right-hand side of that resistor. What do I have on the left-hand side of the resistor? No, I don't have 12 volts. It's a series circuit. I can never have 2 resistors in a series circuit. So if I come over here and put this, so if I come over here and put this, right, you understand, and I put that right there, and I put 12 volts right there, and I'm coming over here, is that guy going to drop 12 volts? You're just guessing. What does the voltage drop across a resistor? How do we calculate the voltage drop across a resistor? Well, well, yeah, we could, but we don't know the size of that resistor. What we're trying to do is, you're saying, okay, we're saying that the voltage drop across that resistor, right, is equal to that resistor. Well, we don't know the resistor, so how can we use that formula? So you're right, that the voltage divider formula says VRX equals to RX over RT times DS, but the problem is we don't know what. We don't know what we're trying to do is figure out what RX is. And another problem we have with this is the Zener's resistance constantly changes. So if the load current goes up, Zener current goes down. If load current goes down, Zener current goes up. If input voltage goes up, Zener current goes up. If input voltage goes down, Zener current goes down. So the R of the Zener, so that formula is because that's a formula that we use for a circuit that's got fixed resistance. The Zener is constantly dynamically changing its resistance to maintain this voltage. So that means if this voltage right here, if this current goes up, then it's got to get current from somewhere. So what happens is the current in the Zener goes down. Well, how does the current in the Zener goes down if it's dropping 12 volts? Well, that means its resistance has got to be going what? It's got to be going up, which is really, really neat. So this is the neatest thing. So back in DC, all you looked at was things that were static. Here we're talking about these are solid state. These devices can be dynamic, which means they vary their internal resistance. So you got a diode which has extremely high resistance when it's forward biased and has very low resistance when it's, did I say that right? Has extremely high resistance when it's reverse biased and extremely low resistance when it's forward biased. A resistor don't do that. A 100 ohm resistor is 100 ohms whether you put negative, positive, or positive, negative. And that's what these things are dynamic, right? So their opposition does change depending on the situation. So what we're trying to do is we're trying to calculate, before I can calculate the voltage drop across the resistor, before I can calculate the size of the resistor, I have to know the voltage drop across the resistor. R is equal to what? I'm not deciding. R is equal to V over I. So before I can calculate the size of the resistor, I got to know the voltage drop across. Is it going to drop 12 volts? No, it's going to drop the difference between 12 volts and what's on the other side. Y'all understand that? So this is where we calculate VR minimum. What's the minimum voltage I'm going to put on the left-hand side of that thing? Well, the minimum voltage I'm going to put over there is what? 14.2 volts. The maximum voltage I'm going to put over there is what? 18.4. So what would the minimum voltage be across my resistor? Well, that's going to be 14.2 minus 12. That's Kirchhoff's law. It says the sums of the voltage drops in the series circuit have to equal to the applied voltage. So it means if I got 14.2 volts right there, this is 12 volts over here, then that resistor's got to be dropping what? 2.2 volts. Now, VR maximum, we got to know that later on to calculate the power requirements of the resistor, is going to be my maximum voltage, which we figured would be 18.4, excuse me, minus what? Minus the voltage on the Zener. Yeah, I mean, right? Y'all see that? So somewhere on that formula, you see, it gives you the way of calculating VR minimum and VR maximum. So what would be the maximum voltage that would ever drop? 6.4. Now we're going to use that later on because resistors, I got to know at least two things about a resistor. Well, I need to know three things. What's the three things I need to know to buy a resistor? The tolerance, but that's not the important. We usually list that third, but you're right. The ohm value, right? When you say the size and the wattage, we got to know those three things. We got to know those three things to buy it. If I buy one with a wattage rating that's too high, then I'm wasting money. If I buy one with a wattage rating that's too low, it's going to burn up, and I'm still wasting money, right? You understand? So what we're trying to do is choose the right wattage rating. So it's going to produce the most power when it's dropped, not when it's dropping 2.2 volts, when it's dropping 6.4. So what do we say we need to do to calculate that resistor? So what does it say about RS? What is it equal to? I'm going to have to erase some of this, guys. Everybody okay? So what's the formula for RS? Now look on your formula sheet and you give it to me. Now I know these formulas, right? Because it makes sense to me, right? Okay, so what's the formula for RS? Okay, VR minimum over our maximum current, I the load maximum, and we already know what that's going to be. It's going to be what? 50 milli, and then we got to operate it over the knee. So where am I going to find the knee current for the Zener? Somebody tell me. Where am I going to find the knee current for the Zener? Where am I going to find the knee current for the Zener? In the data sheet. Thank you, Brian. So maybe y'all logged into Blackboard. I'm not. I should have already been. But we should have, this is what I told y'all we're using a 4742A. So it's a, so I'm going to go on the Blackboard. I don't have to go to Blackboard. I got all the data sheets out there, but we'll do exactly what y'all would do. So all the data sheets for everything we're going to use in this class is up on Blackboard. So I'm going to select our class. This guy right here. Then I'm going to go to data sheet, which is right here. And we put that in the main menu just because we use it so much. And we're looking for the 4700 series of Zener diodes. So here's a 4700 diodes. So I needed a 12 volt regulator. So the first thing I would do, these are all 1 watt Zeners. Everybody understand that? So that's the power rating on it. And I'm going to find this guy down here in the data sheet. Let me zoom in a little bit for y'all. So here's the 1N4742. What's the VZ on it? 12 volts. So we say it's a 12 volt Zener. Then we look over here in the knee current. So the knee current is 250 microamps. And like I said, in these data sheets, you're going to run into a lot of incorrect engineer notation. So what they're trying to do on here, they don't want to shift. So what they want to do is they want to label this column milliamps. And that way they don't have to have, now they don't have to put the unit in there more, right? But if they do that, that means sooner or later we're going to have entries in the table that are not correct engineer notation. So IZK is 250 milliamps. There it is right there, IZK. I just lined it up with my 1N4742. By the way, it's an A. 1N4742A. And that's what it says down here. It says tolerances and type number designators. The JDEC. So this is a JDEC registered device. Did I tell you what JDEC stands for? This is a group where people can register open source components. So this guy right here is open source, which means who can make a 1N4742? It's open source. Who can make it? Well, if you had the equipment, you could make one and you could sell them because they're open source. All I got to do is make sure that it meets this specification right here when I make it, right? Does that make sense? JDEC is a Joint Electronic Device Engineering Council. JDEC registers parts, open technology or open source parts. Type numbers listed have standard tolerances of 10%. A standard tolerance of plus or minus 5% uses a suffix of A. So ours is a 4742A. So that means it's got a tolerance of what? 5%. So what's the three things? Zeners are rated, basically they're rated in the three things we look for on a Zener is we look for the Zener voltage, we look for the wattage rating of the Zener, and we look for the tolerance. And then when we calculate that series resistor, then we need that IZK, right? Okay, so let's figure out the resistor. Let's go back to my PowerPoints. So I'm going to put 250 micro. And I'm going to come up here and erase this up here and give you all the numbers. So what's our VR minimum? It's 2.2 volts. Now, for some reason, people want to use this one. So they say it's dropping 14.2 volts. The Zener's dropping 12 volts, and you only got a maximum of 18 volts applied to the circuit. Y'all realize that we can't drop more volts in a DC circuit. We can't drop more voltage than we have applied. Now, when you take AC, you can, but it's because the voltages are out of phase. And if you take AC, you'll learn that. So it looks kind of strange. You could freak a DC student out with in AC. So you can drop, you might have 50 volts AC applied to it, and you drop 100 volts in the circuit. That's strange. But when you do the math according to AC, then you come up and you'll see how it works, and you'll learn that in AC. So what size resistor do we need? What size resistor does this calculate out to be? I'm going to take 2.2. I'm going to come up here and I'm going to divide that by. I'm going to come up here and it's not can't be milli. Can't be milli because I'm taking milli plus micro and dividing into volts. Anytime I divide a number by a fraction, you will come up with a bigger answer than you started off with, right? Oops. So that's 2.2 divided by, open parentheses, 50 times 10 to the minus third plus 250
That's what I said.
times 10. We're not finished yet.
All right, I was.
Times 10, okay,
walking
minus
with
6. Okay. And then I hit that, and I've got a 44 ohm resistor. I don't know if we got a 44 ohm resistor. I'll have to go. We might have to lower our current down sometime. We don't have a 44. Oh. In fact, there's no such thing as a 44 ohm resistor, so what do I need to do now? Everybody with me so far? They want to see me? Dang it, Rich. Sometimes being in a wheelchair my wheelchair gets caught on things all the time. Okay, guys. So what do I need to do? Huh? And this is, and what we got to think about, is that what we did, we just calculate. So here we come over here. This is the reverse bias. This is called the knee. So we just calculated a resistor that would put me right there, right at the knee. Now, which way do we want to go? If we go this way, we go out of regulation. If we go this way, we regulate. So this is IZ. This is Zener current right here. So do I want Zener current to go down, or I want Zener current to go up? Huh? Down. So if I go down, it's going to move this way. Okay, so here's IZ. So what we're trying to do is we're trying to operate it at a current that is greater than the knee. People say it's above the knee, but that's what they mean, above the knee current. So I need more current. I don't need less current. I need more current. So we calculate, when this came out, we calculated about a 44 ohm resistor. And we never, in Zeners, you never use the resistor you calculate. Never. Because you got a 5% tolerance. So even if it falls on a resistor, you don't use that resistor. We want more current. We want a resistor that's what? Bigger or smaller than what we calculate? Huh? Bigger or smaller? Smaller. Brandy says smaller. Everybody agree with that? If I choose a smaller resistor, that's going to move us away from the knee. Not into the knee. It's going to move us away from the knee, right? Okay. So I need to choose a resistor that's smaller than what I calculated. So what size am I going to use? What do you think? What size am I going to use, Courtney? What do you think, Charles? That's me. How in the heck am I supposed to know? If I know what resistors they make. If I know what resistors they make, then I can choose a resistor. Right? You understand? So what chart did I give y'all? I gave y'all a standard resistor chart. It's in the handout section of the, so find me a standard resistor that's lower than 44 ohms. I don't even know what a standard resistor is. I know what I got. I know what we're going to use. I do have one less than 44 ohms. It wouldn't surprise me if it's not the right one.
Yeah. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%. 2%.
Now what's lower than 44 ohms? What's the next size? Huh? Is it on the chart? 40 what? Okay, so let's look at 43. 5%. We cannot go above 44. So let's say, Courtney said the next one below that is 43. So I'm going to say 43, and it's a 5% resistor. So I'm going to say times 1.05. And if it comes up to be greater than 44, I can't use this resistor. What do they come up and give me? Okay, so we can't use this, right? Because this would be a situation where I use this resistor right here, and sometimes it would regulate and sometimes it would. So what's the next standard value? What's that? 39? We don't have 39. But 39 might work. Let's see. So 39 times 1.05. Y'all know what 1.05 is, right? It's 1.05. That's 5%. What does that come up and give me? What's that? 40.1. So we could use that one. Problem is we don't have one. So what are we gonna do? I got a 33 ohm resistor. That's the only thing I got. And it's a 5%, but it's 6.5 watts, so I don't think we're gonna burn it up. So we're using a 33 ohm resistor. But you see why the 43 wouldn't work, right? Yes, everybody okay? Yes or no? Okay. So now I'm going to come up here and I'm going to use a 33 ohm resistor. That should move us away from the knee. That should be fine. So what's the next thing I should do now that I've chose a resistor? So we're through with this. We're never going to you never use the resistor you calculate, right? Even if it fell on 43, we would not use the resistor. We always do what? We round it down and check the tolerance. If you look at your data sheet, I think that's what it says. Round it down and do what? Check the tolerance. Okay, guys, what's the next thing I need to know about my resistor? 33 ohms. What's the next thing I need to know before I can buy it? The wattage rating. Okay, so what do I need to do to calculate the wattage of that resistor? These are all DC. So all the formulas we use so far, what formulas, where did y'all learn these formulas at? DC. All we're doing is Ohm's law, we're using Watt's law, right? And we use Kirchhoff's law. So PRS. What formula we're going to use? Voltage max squared. It's V squared over R, right? That's one of our power, yeah, V squared. So I'm going to come up here and use 6.4. Y'all know where the 6.4 came from. We're going to square that, and we're going to divide it by the resistor we're using, not the one we calculated. So what's the wattage we need for this resistor? I'm listening. 1.2 watts. Everybody get that? 1.24. And I told you about the power supply class I taught, right? Where they was going to load it down with a 100 ohm resistor. And they just went and got a 100 ohm resistor. And what would they do? They was burning them things up. And they came out and said something's wrong with my power supply. It keeps burning up these resistors. What did they ever do? They didn't calculate the power. So I've got a 6.5 watt. Think that'll work? Huh? 6.4 needs to be what? 6.4 squared divided by 33. That's 1.2 watts. I was fixing to say, good gracious. Normally what we do is we double this. That's watts, Rich. But I'm using a 6.5 watt resistor, so we're okay. Okay, guys, y'all go take a break while I wire this up. 10 minutes, right? Up here, but it's around 15 volts. I've got a meter now across the output, across the Zener, and then of course I still got my meter right here. We're using it to measure current. We'll come to be real careful. We're going to exceed the wattage rating of the Zener, so we won't leave this on very long, and these are the only Zeners I got. So what would be the wattage rating? What would be the wattage rating I would have to use for this Zener? So we know the voltage, so my power of my Zener, I know it's going to be 12 volts. I know we're going to use V times I, right? Because we've given V. So all we got to do is find the current flow through the Zener. So what we need to do is we need to figure out when the maximum current flows through the Zener. Now what the Zener sees is it sees the difference between the current. So when I come up here right here, and I'm going to draw positive, by the way. I'm not going to draw electron. I'm not going to draw negative. I'm going to draw it. I'm going to act like the current's flowing here. And then we got current here. So that current flow through that resistor consists of two currents. It consists of the Zener current. It consists of the load current, right? You understand that? So what I can do is I know my maximum voltage that ever be dropped across that resistor is 6.4 volts. If I know the maximum voltage that would ever be dropped across the resistor, then I could calculate the maximum current flow in the circuit. Right? So IR max would be equal to 6.4 divided by 33 ohms. So what would be the maximum current flow in the circuit? What's it going to be, guys? Okay, your calculator. What's it going to be? 194 milliamps. Okay, so I know, but I know 194 milliamps is flowing right there. I'm sorry. Duh. I know 194 milliamps. So if I put my ammeter right here, then it's gonna. If I can put my ammeter right here, it's gonna measure 194 milliamps. But that's not the current flow through the Zener, because Kirchhoff's current law says the sums of the. So what we just did is we calculated the maximum current flow in the circuit, but my Zener does not see the maximum current flow in the circuit as long as I've got a load out there. Now, if I was to come over here and pull this load out, then that Zener is going to have to handle that 194 milliamps. You understand that? But as long as that load's in that circuit, then the Zener won't see 194 milliamps. What's it going to say? So what we're going to do here, we're going to calculate this right here. So it's going to be times, and then we know it's going to be, we can use R, we can use VRS max. Everybody follow this, if I lost anybody. Divided by RS. That gives me the total current in the circuit. But what would be the current flow through the Zener? So what would the current flow? So let's say I put a voltage in. Let's say I put maximum voltage in, 6.4 volts. And I'm over here, I have the ability to adjust this current. Well, what happens when I increase the current in the load? Well, I've always got right now I got 194 milliamps right there. So what happens to the current in the Zener if I increase the current in the load? Kirchhoff's current law says the sums of the currents into a junction has to equal to the individual currents on the branches. So if the current in the load goes up and the current in the circuit is not changing, then what's got to be happening to Zener current? It's got to go down. That's exactly right. So if the current in the load goes down, Zener current goes up. If the current in the circuit load goes up, Zener current goes down. So Zener, and this is what we're talking about, guys. That Zener resistance is not fixed. It is constantly varying to try to maintain what? To try to maintain 12 volts. So that's a good test question. So what happens when load current goes up? Zener current does what? Goes down. Well, what happens when load current goes up? I just said that. When load current goes down, Zener current goes up. When load current goes up, Zener current goes down. Well, what happens when the input voltage goes up? Well, when the input voltage goes up, let's say my load current don't change. Well, if my input voltage goes up, that means RS has got to drop more voltage. If RS drops more voltage, then the current in the circuit's going up. Well, if the load current's not changing and the current in the circuit goes up, Then what does Zener current got to do? Circuit current goes up, load current don't go up. Load current don't change. Circuit current changes. So if the input voltage goes up, Zener current goes up. If input voltage goes down, Zener current goes down. So the Zener current is varying in the same direction as input voltage, and it's varying opposite of the load current. So this sucker's sitting there changing its resistance all the time. But we can't look at it on a delta or a dynamic situation. We got to say, okay, what would the maximum current in the Zener be? Well, the maximum current in the Zener would be when the input voltage is maximum and the load current is minimum. That's when the maximum current in the Zener would be. So if I unloaded this thing and the input voltage was maximum, that Zener will try to conduct 194 milliamps times 12. How many watts is that? 194 times 12. How many watts is that? 194 milli times 12. 2.3 watts, and it's only a 1 watt Zener, so what would that do? Burn it up. So that means I can't, if I adjust this, the minimum we'd possibly have is 100, but I'll never do that. What would the wattage rating if we limit it to 25 milliamps? So 50 milliamps, 25 milliamps would be the minimum. What would that be? 25 milliamps minus 194 minus 25 milliamps times 12, what would that be? Still going to be high. We're going to be careful. So we don't have any Zeners bigger than this, so we'll just watch out for it. So the formula is VRS max over RS minus, Yeah, two. Minus I of the load minimum. Is that the formula that's in the formula sheet? Or close to it? So you learn all these formulas back in DC, and hopefully you learned them, you know. And all we're doing now is just applying it to something that's dynamic, that has what we call a delta that can actually change. So we'll be real careful when we load this thing down, because I could burn it up. It's only a 1 watt Zener, but we got a bunch of them. So that's the only option we got, or we redo the whole circuit. So this is our circuit. Oops. So it's all crammed in here. I know it don't look pretty, guys. Here's my 6.5 watt resistor. Here's my Zener. I have the cathode turning toward that. Then I have my load in parallel with that, right? You understand? This is the voltage across my Zener. It's a 12 volt Zener, and what's it measuring? This is the voltage across the Zener. It's measuring what? 12.6. This is my current across, this is my voltage across a 100 ohm resistor. So we just multiply this times 10, right? So, and call it milliamps. So that's, we're looking at 26 milliamps right now flow through the Zener. And I'm going to have to be real careful about going down because I could burn it up. I'm going to come up here and increase the current. Oops. I went out of regulation because I went up to 10 milliamps. We designed this around 50 milliamps. So I'm going to put 5 volts up there. By the way, going above the current don't hurt the Zener. The Zener current goes down. As load current goes up, Zener current goes down. But you saw it drop right into the knee, right? See it go up into the knee and it went out of regulation. But this is maximum current right here, which we've designed it around 50 milliamps. Now well, it's going to be hard to get, guys. Well, it's only a 10K pot, so you have very little, got to be real touchy here. In fact, you probably better go this way. Might be what we get right here. Okay, I'm talking fine. So that's 40 milliamps. And what's the output of my power supply? 12.5. Hey, 12.5. And then I'm going to come back and I'm going to unload it down to 20. I don't want to go below 20 because we might burn the Zener up. So what we want to do is get the percent regulation. Ooh, I almost had it. There's a pot. It's not real good. So that's about the best we can do. So at 4.4, it's measuring at 44 or 45 milliamps, it's measuring 12.6. Y'all write that down. Uh, 47, 48, it's getting up there now. 40, so that's 48 milliamps. Because what we're doing is we're putting this, we're measuring across the 100 ohm resistor, right? You understand that? So all I have to do is multiply that by 10 and call it milli. So that's 48 milliamps, and that's real close to what we were shooting for. Okay, and what's our output voltage? 12.6. 12.35, I'm sorry, 12.4. And then I'm going to drop it down to 25 milliamps. So 2.5 volts. And it's 12.6. So it only changed how many millivolts? How many millivolts? About 200 millivolts. So the output only changed. And when we talk about regulation, we can't get perfect regulation, right? You understand that. But my input voltage is changing, my load current is changing, and this guy here is maintaining a pretty constant output. This is my scope across my Zener now. See, it's flat now because we've taken out the ripple voltage is still there, but we're regulating below the ripple voltage, right? You understand? So what we're doing is we're regulating below that minimum voltage. We're regulating below that. And then this is across the Zener. I'll get across that. And that's DC. And that's what we call regulated DC, even though we can't get perfect regulation. And we call it a percent regulation. Are we okay? Yes or no? So we designed our first regulated power supply. Maximum current we could get out of this thing is 50 milliamps. So we could run a little tiny 12 volt motor, no problem. The problem we have with Zeners is that we can't get enough current out of them without burning them up out of the power supply. So what we're going to look at later on, the next thing we're going to get into is something called a bipolar junction transistor. And what we'll find out is we can take this voltage into a transistor, and then we can get tons of current out of the transistor. So a transistor is a current amplifier. It don't create current. It amplifies the current. It gives us amplification on what we can get out of the Zener, right? You understand what I'm saying? Yes or no? Okay, and that's what we'll look at next. So we got a lab we'll do this. So we're going to go to lab now, the rest of the class. And I think most of y'all are working on your unregulated power supplies. And then I think y'all doing filters on there, right? And then put the filter across there. And then when we get through that, we'll do the Zener regulated power supply, and that is not in your textbook. That'll be a handout We're okay? All right, guys, let's go left. Congratulations, first senior. Yeah, that 39 ohm resistor would have probably been a lot better. Whew. The Zener's starting to get. And we don't have any 2-watt Zeners.